Hello. Let's do another simultaneous move Nash Equilibrium calculus game. So the problem is in front of you, and this is different than the one we did in the last video because now each player has to worry about what the other player is going to do. If you think you know how to solve this, or even think you can make a bit of progress on this on your own, why don't you pause the video and do so. In this game, player 1 has to maximize 2ab minus a squared, but player 1 will treat b as a constant. That means when we apply the rules of taking derivatives, you'll act as if b is a constant if you're player 1. Now this makes sense. If you were really playing this game with someone else and you were player 1, you would write down your value of a at the exact same time the other person is writing down their choice for b. You'd both do so secretly and then reveal. So what you write down for A can have no influence on what the other person's going to pick for B. Now it's true what player 2 picks for B is going to be dependent on what he thinks you're going to pick for A. But that's different from what you actually pick for A. So what you write down for A can't influence what player 2 thinks you're going to pick for A. So what you choose for A does not influence what is going to happen with B. So the change in B over the change in A is 0. So again, player 1 will treat B as a constant. So when applying the rules of taking derivatives, again, you just pretend B is a constant. If that confuses you, just put in some weird number for B. Pretend B is 13.8, take the derivative, then go back in and put in b for 13.8 and you'll have the right answer. All right, so we take the derivative of this, treating b as a constant, and we set it equal to 0. That gives us our first order conditions for maximization. So again, we take the derivative of this, treating b as a constant, set it equal to 0, and we get here. Now that is solved, if you can see, as a equals b. Then we take the second derivative, right, we take the derivative of this again with respect to a, treating b as a constant, we get -2, which is negative, so we found a maximum. Let's explore what this means right here. This is saying that player 1 wants to set a equal to b. So player 1 has to worry about what b is going to be. And player 1 can't figure out his optimal strategy until he's figured out what b is going to be. But player 1 is always going to want to match B. So from the point of view of player 1, before player 1 thinks about what player 2 is going to do, player 1 is going to, he's going to do this, and he's going to say, the choice of A that maximizes my payoff in this game is going to be setting A equal to B. So if player 2 is going to set B equal to 38, I want to set A equal to 38. This is player 1's reaction function. It's a very simple one, but still it's his reaction function. It's player 1 saying, once I figure out what player 2 is going to do, this tells me how to react. Another way to look at it is to say, player 1 will regret his choice of A unless A equals B. So remember, in a Nash equilibrium, it's a Nash equilibrium if after both parties see the outcome of the game, no one regrets thinking I could have done something better had I only known what the other person was going to do. So if, for example, it turns out B is equal to 11, but A equals 9, player 1 will say, ugh, I regret this, because had I known B was equal to 11, I would have picked A equal to 11. So this equality gives us a necessary condition for finding the Nash equilibrium. Now, of course, there's lots of ways of satisfying this equality, also keeping in mind that both A and B have to be positive. But this is one condition for solving the Nash equilibrium, because if this doesn't hold, player 1 regrets his choice of A. All right, now let's turn to player 2. Player 2 will maximize his payoff, but now player 2 will treat A as a constant. See, player 2 picks B, but player 2 has no influence on A. Again, as before, What player 1 thinks player 2 is going to do will influence A, but what player 2 actually picks for B won't influence A. So when player 2 takes the derivative of his payoff, he's going to treat A as a constant when you go through the rules of calculus. So this is kind of weird in the Nash equilibrium, that what's a constant or what's a variable differs depending on who the player is. So for player 1, A is a constant. Sorry, for player 1, A is the variable and B is the constant. But for player 2, B is the variable and A is the constant, because the thing you control, that's the thing that's the variable. Okay, so we take the derivative of this with respect to B, treating A as a constant, and we get 8 minus 2AB. Then we set it equal to 0 for our first order conditions. And, if you solve this for B, you get B equals 4 over A. Now we have to check second order conditions. So we take the derivative of this again, and we get negative 2A. But recall one of the conditions were that A has to be positive. So that's just an assumption of the game. The players can only pick positive numbers. So this, of course, makes that negative. So this does satisfy, this will give a maximum, not a minimum. So this is player 2's reaction function. Player 2 will maximize his payoff if he sets B equal to 4 divided by A. So if B is not equal to 4 divided by A, player 2 will regret his strategy choice, and we won't have a Nash equilibrium. So we've got now two conditions for the Nash equilibrium. So player 1 won't regret only if A equals B. Player 2 won't regret only if B equals 4 divided by A. Well, look, we've got two equations and two unknowns. So, most of the time that results in just one solution. And in this case, it occurs if A equals B equals 2. And you can see, of course, if A equals B equals 2, this is satisfied, and we have 2 equals 4 divided by 2, which is also satisfied. So this gives us a Nash equilibrium. Let's just check graphically that neither player regrets his choice. So if B equals 2, player 1's payoff is this. I've just put in 2 for B. We can graph this function where this is A and how high up is player 1's payoff, and you see this is maximized at 2. And let's do the same for player 2. Now I've got player 2's payoff, but I've put in 2 for A, and we graph player 2's payoff, and we see this is maximized at A equals 2, gives the highest value for player 2's payoff if A equals 2. So with this type of Nash equilibrium game, to review, you treat the other person's choice as fixed and unalterable by your choice. And you have a Nash equilibrium if you don't regret what you do, given that you can't affect the other person's payoff. Thank you.